Uh, Good afternoon, everyone. My name is Cheng from Microsoft. Thanks to my colleagues Joe and Lowe introducing the VQA and the captioning set. This session I will introduce how to use text to generate image. So this topic become more and more popular in recent years. And you can see this topic is reverse the task of Lowe's task. My session will last 30 minutes from 3:10 to 3:40, including the Cohen sections. So as JJ mentioned, after the day, we will upload the slides and the recorded videos to our external website. We divide the topics into 3 parts: text to image synthesis, text to video synthesis, and also dialogue-based synthesis. And in each sections, we briefly introduce the task, the dataset, and also the evaluations. And we'll also introduce some of the state-of-the model design for each method. Hopefully, after this tutorial sections, you can have a brief idea or general idea about these topics. Before that, one of the fundamental technology using in text-to-image or just image generations is generated modeling. So far, we have seen many great models which can generate release the data from a traditional Boltzmann machine to some autographic model like pixel RN or CNN to the variational autoencoder VAE and also generative adversarial network GANs. Let's first introduce GANs. GANs have 2 components: the generator and the discriminator playing a min max gain. The generator is to generate the image, and the discriminator is to measure the divergence between the generated data and the real data. The generator is optimized to minimize the divergence. Also, we have VAE, also have 2 components, the encoder and the decoder, forming an autoencoder-like framework. Different from the vanilla autoencoder, the variational encoder have post a prior on the latent space and also use that to regularize the training to get a better performance. The whole VAE is to maximize evidence of a lower bound. As we know, for image generations, VAE and GAN have achieved a great success. For example, the Staggering paper last year showed GANs can generate a very realistic photograph image. Also, we have the VQA work. It can show the same similar performance to face generations. The work we introduced today for text-to-image generation have been built upon those models, either GAN or VAE. Besides the unconditional generations, we also see many famous work for conditional generation, like the cycle GAN and the pixel P2 pixel GAN work for image-to-image translations. Last year, we have seen these speed normalizations further boosted the image generation quality to higher levels. Also, this famous disco GAN, which can close the gap between the image-to-image generations in different domain. Then the other works for unconditional image generation using different resources, like the image generation from SceneGraph, the image generation from audio and speech in 2019, and also recently people are more interested in doing image generation from object layout or silent object out. After seeing these examples, a natural question is, can we do image synthesis or generation from text description? The answer is yes. And we can do it using a very simple conditional GAN or VAE framework. Here is a simple framework using conditional GAN. The input of the conditional gain is the text distribution and the real image. First, we encoded the text distribution into hidden vectors. Then we concatenate the hidden vector and the random noise into a vector and put it into the generator. The generator uses that to generate the image, and also the discriminator is do the same thing to measure the difference between the real image and the generated image. By doing this, we can achieve this task. But beyond that, we have seen many like great work in this area to for text to image generation, like 2017 Staggering, 2018 Availing and Tailor, 2019 Object Gain and Mirror Gain. Also this year CVPR many gain. Here is the example of image generated using conditional gain. The model takes description, red flowers with black centers, and general with a flare-like image with some like black regions in the middle. You can see the generation quality is okay, but if you see other dataset or generated examples, the quality is not that good, right? You can see some blur regions in some of the image. Also, as I mentioned, conditional VE another powerful tools for the text to image synthesis. This work tries to generate the text image from the text attributes with conditional VE framework. You can see on the face and the birds datasets, they can do very good job. To get a better generation quality, we have seen this Staggering was proposed. The key idea of Staggering is to do two-stage generations and generate the image progressively. In the first stage, it tries to just generate some like a roughly structure of the image with lower details. And then in the second stage, it's just more photorealistic image with high details. In both stages, the text input were they will take the same text input as the conditioning. Let's get more details about the Staggering. At the first beginning, we will have this image first downsampled to some smaller image, and in stage 1, it generates image from the text input, and the discriminator also measure the difference between the generated image and the downsampled image. In the second stage, it first fusion the feature map of the first generated image and the text description into one vector, and using that to generate image. Also, the discriminator is measure the discrepancy between the real original image and the second image, the generated image. Here we show some examples generated from Staggering. You can see the first line is the generated examples from the stage 1. It roughly give you some like the size and the colors of the birds, but it looks very blurred. But in the second stage, you can see you will get a more realistic image with some details like the color change in the head or different stuff. Still, in some region, it's not very clear, like this one or this one. Still looks blurred. Also, Staggering have the second version called Staggering V2, use more generators and discriminators. Due to the time limitation, we were not introduce it here. If you are interested, you can look at the paper. After Staggering, another good job called Attention Gain is also proposed in 2018 by my colleagues in Microsoft. The key idea of attention gain is pay attention to the relevant words in the description and the region in the image. By doing that, attention gain can capture both global sentence level alignments with the image and also the fine-grained word level information from the text. Here is the framework of the attention gain. We can say it still adopts the Staggering to multiple stage generation trick, but different from that, in each step, it's not just use the text description adding the round noise, but it also have some attention work between the text, the generated regions and the word features. After this attention step, you will have the attention feature map concatenated random noise for the next stage generations. Also, you have another very important component called the semantic similarity matching modules, which matches the similarity between the final generated image and the word description. This module is very important. Actually, it's play regulator to guarantee attention gain can generate a very good image. Here we show some examples for attention gain to analyze attention gain. First, we show the attention map. You can see when we bridging the relations between the words and the image regions by the attention, you can see each word will align with some region of the images for the generations. That is what the key point of attention gain. And also, we can see different from the Staggering, attention gain can also generate like some object with more details. Like in these examples, the sentence mentioned something like pasta or Berkeley, and in the final images, you can really see pasta and Berkeley's. Also in this second example, showing the similar stuff, it's mentioned bananas and wikis, and you can still see similar stuff. These slides show more examples when compile attention gain with other framework like Staggering version 2. And we can say in the both dataset, this COB is the bird dataset I just showed, and this COCO dataset is COCO image caption dataset. We can say measured by FID and inception goal, attention gain all outperforms other baselines. And also you can see these examples and on the birds dataset, actually the generation quality is near perfect. But turns out the more complicated COCO dataset, the generation quality is not that good. It roughly have some objects or background there, but not very detailed. Following the attention gain framework, lastly we have this mirror gain. It's roughly take over the attention gain framework, but added another path. Instead of just having the text to image semantic similarity matching, it's also generated the text from the image and measure the similarity between the two texts. Follow a closed loop between text to image and image to text. By doing so, mirror gain can show a slightly better performance than attention gain. Okay, let's have first stop here to summarize the text to image synthesis framework. We have talking about the dataset used in this domain, like the COB, the birds dataset, and the first data I show the flower dataset, and also the COCO captioning dataset. And we can see the current method following Staggering or attention gain can do very good job on simple dataset like birds and flowers, but not on complicated ones like COCO. Also, we see the evaluations. We saw this almost the same following the unconditional gain or VAE generations, like using inception score or FID scores. Also, sometimes we saw it's have to do human evaluations. And talking about the technical challenge in this domain, I think first is can we find a better like evaluation metrics instead of the traditional inception score or FID or human evaluations. And the second one is I look at all the current GANs. I think it's try to learn the discrete mappings between different attributes to the image, like the color, the objects, and the size, and some other attributes. But when we think about the more larger data sets with a larger vocabulary, like MS COCO, this training will become very difficult. And the third challenge comes from the multi-object generations. As we can see, the reason we can do very good job on the birds or flower data is because they almost contain one object and a simple background. But how can we handle some data set like COCO with multiple objects, and how can we model the relations? I think ObjectCAN is first proposed to solve this challenge, especially modeling the multiple objects. Instead of do one-step generations to match the real image and the fake image, the ObjectCAN have another loss, try to match the object layout to the real layout. And by doing so, you can say the ObjectCAN can do a better job than both Staggering and Tailor by do some like object generations. Also, another work in the same year proposed called object pathway. It's not just handle different objects, but also it's modeling some implicit relations between different objects using a framework called object pathway. By integrating this object pathway, you can say the object pathway GAN or VE can generate very good examples. Like for the first examples, the description said 2 regularized sliced pizza with multiple toppings. Actually, this is the real image, and the second one is generated by the object pathway GAN, and third is by the attempt GAN. You can say actually the object pathway GAN can generate the 2 actually pizzas on some toppings, which is very good. Then we proposed another slightly different task called image manipulations. Different from the text to image synthesis, which is quite straightforward. This one giving an original image, like these 2 birds, and giving a text description to describe the ideal image with the original image. Then the generator will generate image to reflect the difference between the original image and the generated image by this sentence. We saw that Tailor is the first one for this task, and actually did quite a good job. And this year we see this mining GAN. It have 2 components. First is called the Availing combination models, which give you some like roughly generations for the whole image, and also is have the detail correction models, which just change some portion of the image to get the final goal. By doing so, we can the mining GAN can slightly get better performance than Tailor. Okay, after the first section, the text to image synthesis, we were into the second task called the text to video synthesis. So the input is still text description, like playing golf on grass, but the output will be a short video clip contain multiple frames. First, we need the content between the generated videos and the sentence be closer, And also we need the consistent between different generated frames. That's the goal of this task. The T2V framework was the first one to propose for this task. I think it's relatively simple, just using a conditional VE framework with some like traditional CN encoders, iron encoders to encode the whole sentence. To ensure that the consistent between different frames, it adopts a component called Keyst. Keyst, you can see Keyst is the image layout designer to keep your image or general frames to be consistent. And after all, it's not measure the similarity between frame and frame. It's actually measure the similarity between the whole frames and the real frames. Here's some example generated by T2V. We can say roughly it can ensure the generated content, which is consistent with the description. And also we can say have some coherent between different generated frames. But still the generation quality is not that good. It still has some blur image. Then in 2018, the paper called TF-GAN, Improving Conditional for Text Video Synthesis, using not VE but the GAN, Conditional Gain framework to do such task. I think one thing to mention is also use multiple GAN framework, but using this convolution filter generations to further boost the performance. And we can see that there's some comparison between the T2V VE framework and the TF-GAN framework. By using TF-GAN, we can get better generations for for each frames. Also keep the consistent between the text description and the coherent between different frames. After talking the original or vanilla text to image to video synthesis, we come to the new task called story generations. This is slightly different from the text to video synthesis. The task is first to give a paragraph of sentence, not just one sentence, and try to generate different frames based on each sentence. It forms a one-to-one mapping, one sentence to one frames. But overall, you should keep some coherence between these generated frames to form stories. Also, you should have this whole generated frames to be consistent with the whole paragraph. That's an even harder task than the vanilla text to video synthesis. The framework looks like this. First, for each single frame generations, we're embedding the noise epsilon with the text description. Also, to keep some consistency, we use the so-called Keyst components. And also, to ensure the global consistency between the whole frames, we're embedding the whole stories with the encoder and embedding the whole story in each frame before going to the generator. To measure the loss, we have two discriminators. One is called the frame level conditional discriminator, just measure the discrimination, the difference between the real frame and the generated frame. And then we have a global story discriminator, which can count all the frames together with some CNNs and measure the difference between the whole video frames. This is a brand new task. So we proposed some new data set for such a task. The first one is we collect from Clever. We use the Clever simulator to change one attributes each time, like the location, the size, and the colors of different objects. And then we form something like the sequentially clever versions. You will see some difference between each slides. And you can see our model can do better like image generations compared with the Staggering. This example shows some like coherence for of the generated images. Like we model can change, can make coherent generations between frame by frame. Also, we have the parallel dataset, which is more realistic dataset using the cartoon image and also some paragraph. You can see story can also achieve some very good generations giving these paragraphs. But the one problem is that the story can have some difficulty to generate very good person or like object details, like the cartoon characters in each frames. But for some others, like common used objects, I think Stockgan actually did quite a good job. Okay, let's move to the last section about dialogue-based image synthesis. The motivation of this task is we have seen the task called image manipulations, which use language to guide the image generations. And we can say some like dialogue-based image retrieval. Basically, in each dialogue turns, you will get feedback from the users, and you will retrieve one or like top image based on the feedback. So the question is, can we do similar stuff like the dialogue-based image retrieval, but using more instead of doing retrieval, we're doing generations? I think it's a very interesting task. So people have done many work for the benchmark effort. As the chat crowd dataset, they try to manipulating the size of different objects, but it's very simple objects in the image, and collecting this kind of dataset. And also the neural printers, they try to do some like image editing using multi-turn dialogue, but they have difficulty to get the data set. So as a result, finally they try to turn this birds or flower data set for the training, and they form this like a sequentially GAN framework, but they have some trick to adding some like a random noise or random population in each stage to make this more robust to sequence generations. And also we have seen this framework from Mila. They form a new dataset called chat painter for multi-turn dialogue generations. The motivation here is slightly different than the motivation we mentioned before for the dialogue-based generations. Is they think that if you just generate image based on one captionings or one sentence, like those captionings, it will roughly give you some very some similar images, but with different styles. So in order to get more information for the generations, you need to ask more detailed questions, like this is not just the birds in the sky, but it's also have other stuff like the buildings and different backgrounds and the color of the sky. So after you're collecting all the feedbacks of where the dialogue turns, you can generate based on those dialogues, which will give you different generation results for the two. In the method part, I think they just use the traditionally RN or STM stuff to encode all the dialogues for the final generations. Also, so last year, the Facebook and Georgia Tech have this CoDraw dataset. Particularly, they form a two-player game in a goal-driven collaborative task. One is called the Tailor. The Tailor would say the ground truth image and tell the difference tell the drawer to draw different objects in the cartoon dataset, while the drawer will receive these informations and put different objects based on the feedback of the Tailor. They form this platform and collect the dataset. Also, they use some very regular deep learning blocks to model the drawer and the Tailor separately to get some model done. We also propose another framework called Sequential Gain. As I mentioned, the dialog collection for the image is very difficult. Instead of try to collect the dataset in a diagonal way, we first divided the image sequence into different turns, and then we only ask the Human annotator to provide the difference between two consequent images. Then we summarize all the sequence to a dialog form, and using this sequential gain framework to do the modeling. This sequential gain modeling is an extension of the gain. The only difference is in each step we'll have different dialog input and to do the generations. Also, we will measure the global difference between using the discriminator instead of one single image, and also use this semantic similarity matching to guarantee the training framework getting on well. And you can see we compose with different methods with our sequential gain, from gain and gain, and also Staggering. You can see our sequential gain can get some better generations when consider the consistent with the text description and the coherent of different generated images. Okay, I think I have finished all the methods regarding text to image, text to video, and dialog to video synthesis. Let's put one slide to summarize the text of dialog to video synthesis. I think this is a very interesting domain and tasks, but we have seen like many studies in recent years to pay more attention to the problem definitions, the benchmark efforts, and also we have seen some like modeling results. But still, this is a long way to make this problem is not even to production, but to complete the research problems. The first is all this is somehow based on some dialog data or some video data. We first need more effort to do more benchmarking efforts, because as we know, collecting the real dialog is very difficult. And also, I think that in most of the paper I have talked about, they also use the inception goal and FID or some human evaluations. We still need some better way to do all the evaluations. Also, in the modeling side, we still need to consider several modeling techniques like how to do consistent generations, how to discount the learnings to know the difference between the words and mention different regions, and also sometimes do some compositional generations. I think I have finished all the content. Let's go to the Q&A section. Thank you so much.
Hi, you got 3 questions from the audience right now. The first one is, what are some promising directions